Hey guys, so welcome to another video on complex analysis. And yeah, let's begin. So, complex analysis. Well, let's us first introduce complex numbers. So, when we talk about real numbers, we're talking about one number axis, right? The number line, right? Can take negative numbers, positive numbers, zero, right? But now we generalize 2D. So it's like complex number is basically essentially a 2D number, right? And you can represent complex number using Euler's identity. So one way of writing complex number is writing it in terms of its real part and its imaginary part. So z equals to x plus iy, and x is the real part of our complex number, and y is the imaginary part of our complex number. Or we represent it in a polar form. We represent our complex number in terms of its magnitude and its phase. So z equals to x plus I1 also equals to r times e to the power of I theta. Now let's recap about functions. So f of x equals to x squared, where x only take real values. This is one of our functions. So you can see from this mapping of sets to visualize the function. So 1 gets mapped to 1, root 2 gets mapped to 2 because root 2 squared is 2, 2 gets mapped to 4, negative 1 gets mapped to 1, and pi gets mapped to pi squared. Right. And now for g of z equals to z squared, what we did is we merely generalized our previous function. But now for our domain, we're going to consider the entire complex plane, where we used to only consider the real axis at the start. So now our input can be any complex number. So 1 plus I will be a valid input. And if we do 1 plus I squared, we actually get 2i. So 1 plus I gets mapped to 2i for our complex functions. And 2 plus 3i, that example, if 2 plus 3i squared is basically negative 5 plus 12i, right? So it's essentially the same idea, right? Where you map your domain set to your range set. Okay. Now, let's recap about differentiation. So recall when we differentiated real functions, right? What we essentially did is that we consider the gradient of the secant line. So suppose you want to find the gradient of the function, right? When x equals to 1, right? What you can do is that you take point that is very close to your point x equals to 1, but not exactly at the point. So it's like very close to it, as you can see, like starting from the left, and you can estimate the gradient for it. And at the same time, you estimate the gradient as you approach the point x equals to 1 from the right, right? And if these two gradients are equivalent to each other, which is pretty evident from these two animations, they are the same to each other. So if ml equals to mr, that means the derivative of our function f of x is well defined at point x equals to 1. So this is the condition for our derivative to be well defined, is that as we estimate our gradients as we approach our point from the left, and as we estimate the gradient as we approach the point from the right, if these two gradients are the same, we say the derivative of f of x is well defined at that point. But think of this question: is the gradient, or no, is the derivative of this function well defined at x equals to 1 or not? Is it well defined or not? The answer is no. Why? All right, now let's consider estimating the gradient at that point as we take the point from the left. So we go from left to x equals to 1, right? And our gradient will basically be something like this, right? The line. But if we take from the right, our line looks like this. And it's evidently that these lines don't have the same gradient. So this is an example where ml is not equals to mr. So therefore, our derivative is not defined because it cannot take multi-value, right? So in this case, our derivative is not defined. So let me do a quick summary of what we just talked about. So for a function to have derivative at a point x equals to a, the left gradient approximation must equal to the right gradient approximation. So basically, as we take our limit as delta x approaches 0, so from the negative, so delta x approaches 0 from the negative side, equals to like the gradient estimated by taking delta x from as delta x approaches 0 from the positive side. If these two limits are equal to another, that means the derivative is well defined at the point x. So this is a condition for a function to be real differentiable. Now we can generalize this differentiation concept into complex functions. So let us consider the function f of z, where its domain can be any complex numbers. How do we know if the function f of z is differentiable or not? I mean, we're think of this question at first. What does differentiation even mean when extended to the complex plane? Now, let's consider our real function again. So if a function's domain is taking real numbers, right? Essentially, for example, if I consider a point x equals to a, essentially there's only two directions where you can approach this one. It's either you approach from the left or you approach from the right. There's only two directions to approach a point x equals to a. But for our point in a complex plane, so now let's take the entire complex plane as our domain for our function. There are infinite amount of directions for which you can approach equals to b. You can approach from this direction, this direction, this direction, this direction, this direction, this direction. So essentially, infinite approach directions to z equals to b. Right, b is a complex number, of course. So yeah, so that's something to worry about. So as we recall that for our real functions, we need to consider the gradients from two directions. Well, that's mainly because there's only two directions where you can approach x equals to a. But that means that when we evaluate the gradient for our complex function, does it mean that there's infinite amount of directions of approaching? So we can literally associate infinite amount of gradients for each. So we associate one gradient for each direction. And is it necessarily for us to like verify that the gradients for all these directions must be the same for our function to be complex differentiable as equals to b? All right. So what I mean is that, so recall our differentiation of the gradients, f of x plus delta x minus f of x over delta x. So now it's basically going to be f of x plus delta z minus f of z over delta z. So now, but now I represent delta z as delta x plus I delta y, where delta x is the increment, it's the delta increment of the real value for z, and delta y is the increment on its imaginary part. So x plus delta x plus I. Wait, hold on. Right, sorry. So, right, yeah. So, essentially for our gradient, for our complex function, it's just going to be f of z plus delta z minus f of z over delta z, right? Analogous to our real functions. Now, so as I mentioned, for real functions, there's only two directions. So when estimating the gradient, we only need to consider these two directions, the one direction from the left, one direction from the right. Well, for our complex stuff, it's a bit different. We have to consider like all directions, right? We have to verify that the gradient is the same for all directions, for this infinite amount of directions, before we can assert that the derivative is actually well defined at the point. So yeah, I'm considering like f of z at a point z equals to 1 plus I. So this black dot uh, the second picture is a little bit weird. You know, it's yeah, something like that. Right. So, okay. Now let's consider, all right, let's break down our question. Right. Let's actually check for this direction of approach. So this is an example where delta x is greater than 0 and delta y is equals to 0. Right. So like you approach the point from like a positive real value, and like the imaginary part doesn't change. So using our formula, right? Delta x is greater than 0, delta y equals to 0, right? And obviously, we're considering the derivative at the point z equals to 1 plus I. So x is 1 and y is 1, right? Because we're considering, because z equals to x plus iy, right? So and we're considering the point 1 plus I. So x equals to 1, y equals to 1. Right, so this thing gets simplified to this, and we can expand that, right? We can definitely expand that. These two terms cancels out. So basically what we're left is limit as delta x approaches 0 from the positive side 2 times 1 plus I plus delta x. And as delta x get really small, this last term is basically irrelevant. So our gradient associated with this directional approach is 2 times 1 plus I. Now let's consider another direction. Right, this time our delta x equals to 0, but our delta y is greater than 0. So we are approaching this 1 plus I point from a positive imaginary direction. Right, and we keep the real value constant, right? Because as we approach from this hollow point to the black point of interest is z equals to 1 plus I, like the real part doesn't change. So now let's get simplified to this. So delta x equals to 0 and delta y is non-zero. Right, and obviously, again, x is 1, y equals to I because we're considering the point we're considering the point z equals to 1 plus I y. 1 plus I, z equals to 1 plus I. And if I expand this, right, using similar approach, I also get 2 times 1 plus I. And obviously, I can also check for other directions. And in fact, like if you check for all directions, you will always get 2 times 1 plus I for your function f of z squared at the point z equals to 1 plus I. So now we can conclude that f of z equals to z squared is indeed differentiable at z equals to 1 plus I. Right. And with the same reasoning, it should be obvious that for any complex number z, the derivative of f of z equals to z squared at z is always well defined. Right? Because like why does it need to be 1 plus I? It could be 1 plus 2i, it could be 2 plus I, right? And it doesn't really change our derivation much. Right. And I skipped some directions, like these directions, but like if you find it, you should still get 2 times 1 plus I, yeah. Right. Now it's your turn. Can you try to prove that f of z equals to z conjugate, this function, is not complex differentiable? So when I mean it's not complex differentiable, it means that the gradient you calculated for two different directions of approach to a point is not the same. So for example, when we approached our point from the positive real axis, we got 2 times 1 plus I, right? But maybe that as our approach this direction, as we approach this 1 plus I point from another direction, we get a different gradient compared to the gradient we get for this direction. So yeah, I'm gonna leave you guys some time to do this. So yeah, recall the definition of complex conjugate, right? So f of 2 equals 2, f of 3i equals to negative 3i. So basically the real part doesn't change. The imaginary part the sign gets flipped around, right? Okay. Alright, time's up. So the answer is no. This is not complex differentiable. Um so let's consider approaching our point of interest, right? Because our question is the function differentiable at z equals to 1 plus I or not? So our x is 1, y is also 1. We're considering the point 1 plus I. As we approach our point from the positive real axis, so this is an example of delta x greater than 0 and delta y equals to 0 because the imaginary part doesn't change, right? We evaluate our gradient, so it's basically a substitution of that. So recall that f of z is just z conjugate, right? So it's like, so delta y equals to 0, so it's just gets simplified into 1 plus I plus delta x conjugate minus 1 plus I. And so this is basically just 1 plus delta x minus I, right? Because the real part doesn't change, the complex part changes. And in the end, it will simplify to 1. Yeah, and this derivation should be quite straightforward, so I won't talk about that in details. So now let's consider a second test where now we approach our point of interest 1 plus I from the positive imaginary directions, right? So delta y is greater than 0 and delta x is equals to 0. Substituting in our equation for calculating the gradient associated with this direction. So now it's going to be delta x is equals to 0 and delta y is greater than 0. So 1 plus I delta y conjugate minus 1 plus I conjugate over I delta y. So yeah, as we take the complex conjugate, right? The signs for the imaginary part gets flipped around. So it used to be I plus I delta y. Now it's negative I minus I delta y. And we do some cancellations, and we end up with something negative I delta y over I delta y. So in fact, the gradient we get from approaching our point z equals to 1 plus I from this positive imaginary direction is negative 1, as opposed to 1 as we approach our point of interest from the real axis direction. So you get different gradients for different directions. So therefore, you can conclude that f of z equals to z conjugate is not complex differentiable at the point z equals to 1 plus I. Quite interesting, right? So, well, it looks like we need to check. So, to conclude if a function is differentiable at a point, it's complex differentiable at a point or not, it looks like we have to check all directions. But it turns out we don't. We actually do not need to. So, and to prove that we don't, I'm gonna use I'm going to derive the Cauchy-Riemann equation. So now let's recall our definition for the gradient, right? It's m equals to limit as delta x, delta y approaches to 0, f of x plus delta x, which is plus I times y plus delta y, minus f of x plus I y over delta x plus I y or I delta y. So, or essentially it's just f of z plus delta z minus f of z over delta z. So suppose let's only check these two directions first, right? The first direction is delta x is greater than 0, delta y equals to 0, and the second direction is delta x equals to 0 and delta y is greater than 0. Okay, so m1 is basically f of z plus delta x over z. So this is this point 1 plus I is our z, right? Z equals to 1 plus I. So it's going to be f of z plus delta x minus f of z over delta x. And it's basically just our partial f with respect to x, right? Because we're keeping y constant. What we're doing is that we're only varying x. And for m2, it's essentially keeping x constant. We're only varying y, right? But remember, there will be a constant of 1 over I in front because our delta z is not just delta y, but it's in fact I delta y, right? Because if we look at this, our delta z is not just delta y, it's I times delta y, right? Because we're approaching from an imaginary axis. You have to consider this imaginary part. So you have a 1 over I factor in front of your partial f partial y thingy. So I mean, obviously, you need these two directions to be the same. So before checking all other directions, let's first make sure these two directions are the same. Right. That's a condition we know that we must have. And for these two conditions are the same, we basically equate m1 equals to m2. So partial f with respect to x should equals to 1 over I times partial f with respect to y. So, and if I times both sides by I, this is essentially our Cauchy-Riemann equation. So I just derived it. But now, let's say, can we generalize our findings to different directions? It turns out we can by resorting to something called the multivariable chain rule, right? So this is the form for multivariable chain rule. So now, like, let's see, you're going from a general direction. You're not approaching it from like a very special direction, like say delta y equals 0 or delta x equals to 0. Now you're like, let's say maybe for this one, both delta x and delta y are all greater than 0. But you can still find the gradient associated with that direction by representing that as a basis, as a linear combination of the um, of the gradients in the two specific directions. So that's essentially multivariable chain rule. And from the Cauchy-Riemann equation, we can represent partial f partial y with I times partial f partial x, right? We factor the partial f partial x out, so it's going to be partial f partial x times dx dz plus I dy dz. And recall the definition of limits, right? This thing in the brackets can be written as this. And but recall that delta x plus I delta y is essentially our delta z. So this thing gets reduced to 1. So this is also equals to m1. So this basically tells us for all our directions, given the Cauchy-Riemann equation, so given that the gradient associated with these special two directions of the real from approach from the positive real axis, this approach from the positive imaginary axis, as long as the gradient for these two directions are the same, we use our multivariable chain rule to find for a general direction, it will essentially still be the same. So therefore, we prove that for all directions we approach this point, the gradient should be the same as long as Cauchy-Riemann equation holds. So now we consider complex value functions, right? Um, and a function is differentiable at a point z if Cauchy-Riemann equation holds true for that point, right? So this is how we write Cauchy-Riemann equation. So thanks for watching. So that's part 1 of our complex analysis series, and stay tuned for the next sections. And thank you for watching.